Okay, so let's start the class. Remember, you have a assignment that was due yesterday. If you missed the deadline, just shoot me an email, but try to go by the deadline. So before we start, and I just posted a new assignment for next week. So before we start, I want to go over a few things. First of all, someone asked me a question about, I told you that, so if I ask you for the test, how much voltage do we get here? 120 volt, A, AC, very good. But if you go to Europe, it's going to be 220 volt AC. So of course you might ask if you bring your laptop, for example, to France or Italy, is that okay? And the answer is yes. Nowadays, if all you need is a plug adapter. So this is the plug we have in France or in Europe. This is the plug that we have in the US. But the laptop, because they want to sell them like on an international scale, they will sense if you are using 220 or 120. So the power will be the same. If you are using 220, the current will be less. If you are using 120, the current will be more. So that's for the electronic devices that we use like everywhere. However, if you are using like another kind of device that's like a washing machine or something like this that usually you don't travel with, so in that case you cannot use a plug adapter. So you have to use what is called a voltage converter. Okay, voltage adapter. So in that case, and that's what we used to have. So in that case, it will convert 120 to 220. Okay, so some electronic device like a dehumidifier, I don't know if you want to bring that to Europe while you travel. So you cannot use the plug adapter. You need really to convert. But most electronic device like your laptop, you don't have to worry. You just need a plug adapter. So answering your question. So that was a good question. About safety, I want to make sure that I was clear. You see, outside your house or your apartment building, you're going to have a transformer, right? It's like a box here that you see on top of the poles, right? So that transformer will take 10,000 volts, like 7,000 volts, and bring it down to 120 for your house or your apartment. Okay, so you bring down 7,000 volts to 120. So you see, that will be the hot wire. Okay, so electricity is going to flow. So this is 120. It's going to flow here in some device, some gizmo. And then the current, when it's coming back, it's going through the ground. Okay, so the return path is through the ground. So that's why it could be dangerous, because if you touch like a machine, an X-ray machine, and there is some leak somewhere, you are making a path to the ground. So it can go through you and you can be shocked. So of course, all the machine now has this safety feature, so it will also be connected to the ground. However, if you are bare feet, for example, if you don't have a good insulation underneath your feet, if the current has the choice between here or there, maybe it will still go through you. However, if you have thick shoes, like very good insulation underneath your shoes, then you will be fine. But that's how it works. So why is it that they use the ground as a return path to the base? You can think of that as the base. You can think this is like a power supply with a plus and a minus, except the minus is connected to the ground. So that electrode here will have, for example, 7 or 120 volt above the ground once it's go through the transformer. Is that clear? So why is it that the return path is through the ground? Because if you have lightning, okay, if you don't connect it to the ground, if you connect it to your house and then back here, lightning will go and start a fire. If you connect that to the ground, if you have lightning, it will go to the ground. Is that clear? So make sure, even when you do your use your washing machine or whatever, don't go bare feet or don't go in flip-flop. You never know, just to be on the safe side, because people keep moving those machines, so maybe there will be like a short somewhere, just to be safe. Okay, so I wanted to make that clear, especially if you work in hospital. So we're going to talk about transformer, but you can visualize what I meant here. So you have a house. These high tension line, they can be at 1000 volt. Okay. Why do they want to be at so high voltage? Because high voltage means less current. And if you have less current, you don't have to use a very thick wire, so you save money. Before it gets to your apartment building or to your house, you're going to bring that voltage down to 120 or 240, right? Even 240 for the big machine. So that's how it works. And you see, it has to be connected to the ground. So electricity here go through the hot wire into your appliances, okay, to provide power to your appliances, and then electricity go back through the ground, back to here. You see how it works? You see them around here, everywhere, those ugly things here. Okay, so what else I wanted to tell you? So here that was to connect to biology, since most of you are in health science. You see in the nervous system, you have those neurons that talk to each other. So it's not really electricity flowing. It's the signal is transmitted through voltage change. Okay, so I told you you have those ions, potassium, calcium, sodium, whatever, they go in and they go out. So you have a little voltage. So when you have a signal that move along those neurons, it's a voltage change that moves along. Okay, so that's how it's done. And to model that, it only was understood in the 1960s. So to model that, they were able to model a neuron, okay, or other cell in human body with an electric circuit. And that led to a Nobel Prize in 1963. But originally, it was really to understand how neurons work and how the signal is transmitted through the nervous system. So before that, they didn't have a good understanding, and now they can use, a basic electric circuit to model what's going on. Okay, I don't know the detail, but this is sodium, maybe this is potassium. Okay, so at the same time, there was another scientist who understood the neurotransmitters, right? When you have a synapse, you have some chemicals being released, and that was done at the same time. So 1963, there was a Nobel Prize for that. Okay, and what else? So this is called neuron action potential. It sounds complicated, but it just means that the voltage is moving along. The change in voltage is moving along. And we talk about resistance, and I told you that when you have a neuron like this, there is a insulation. Okay, it's like a layer here to make sure that it doesn't leak out, and that insulation has to be very like thick. Okay, and that's called myelin. So maybe you learned that in biology. Have you learned about that? Right, Myelin? Oh, good. See, I'm connecting. And a few people know that it's actually made of cholesterol. Okay, so that's why cholesterol is not a bad thing. Okay, so that was just to connect. What else do I have? Okay, I did that. I did that. Okay, so then we learn about Ohm's law. So for example, here you have a typical circuit. So 9 volt. Okay, so that will be your power supply. So the positive charge will move here along and then deliver the energy to the load. So this is called a resistor. So the resistor will turn electrical energy into heat. Okay, and its job is to limit the amount of current flowing. So Ohm's law says that the voltage drop across a resistance. Okay, so voltage is a property of 2 points. You always have 2 points. So in that case, you only have 9 volts. So what do you think the voltage drop is going to be here? You start with 9. It's like you are falling. 9 volt. How much is available to the load? 9. Okay, there is no other load. It's only one load. So the voltage drop here will be 9. Does it make sense? Remember the schematic I gave you. Voltage is like a height. So you start with a height of 9. You're gonna drop across each load. But here you have only one load. So it's gonna fall 9. Okay, so 9 is the voltage across. Again, it's a property of 2 points. So here you're going to read 9 volts. And how do we find the current? Ohm's law. V equals Ri. Very good. So the current flowing through the resistor will be 9 divided by 5. Okay, so that's Ohm's law. And we are talking about voltage drop. Okay, so it's just a refresher. And make sure when you do your homework that you do it very seriously. You have to you use post-it, you hide the hints. And for the first attempt, you need to do it using your textbook, using your notes, using your slides, using Google if you want. But don't look at the solution, don't look at the hint. And then for the second attempt, you can look at the hint. Otherwise, it won't. It's not going to be digested. Okay. Before I forget, I wanted to show you a nice website here. Okay, so that website, I think it's in Canvas. And especially if you want to take the MCAT, for example, it's a nice summary of everything. And right now we are doing electric circuit here, see? And if I go, so you see everything you need to know. I don't know what that picture is doing here, but here, imagine, so in your house, you get 120 volt. And you know that most houses cannot handle more than 15 amp, 20 amp will be really the maximum. Some places it's only 15 amp. So you have a special fuse. If you try to drain more than 15 amp, the fuse will open, and then you have to come back and turn switch on again. So can you answer this question? So you have a hair dryer, and it says on it the power is 1200 watts. Okay, so 1200 joule per second. And you want to know if it's gonna be okay with the fuse. So can you find the current drained by that hair dryer? So remember, look at your equation sheet. Don't forget everything from one class to another one. Okay, you have to save like special USB key for 2054 and you save. So remember, power is the voltage drop times the current, right? So on your hair dryer, you can read the wattage and it says 1200. And you know that in a house you get 120 volt, okay, for regular appliances, or otherwise a big washing machine and dryer that will be 240, otherwise is 120 times I. So what's going to be the current? 10. So will you be okay? Yes, okay, because it's less than the max. If you reach the max, there is safety measure, so the fuse will break. Okay, so that's a nice website. I think the next one is about resistors. Okay, so these are resistors here, and they have a special color code. So you know the value. But we don't do that anymore. We use a multimeter and it will read the value. Okay, I think the link is in Canvas. Okay, so now you have to remember to remind me where did we stop? 1, 2. Did we do this one? This one? Okay, let's do number 6. So let me remind you that we did number 62. We did all that. Because I forgot. Did we do it or no? First set of problems up to here? Here? Okay. Okay. I don't know. Maybe let's do number 6. No, let's do number 5, just a review. Number 5. Right, by the way, all those problems, you find them in my Dropbox, okay? I go over them step by step. It's a long time ago I made those videos. So this is a load. So you can use P equals VI, okay? So that will be always true. Now for resistance, only you have P equals RI square, which is V square over R. Sorry. It's good I have no one close to me. Not that I'm sick, okay? I'm not sick. 75 equals voltage 120 times the current, right? So the current will be this to 5 amps. And usually we convert that to milliamps. So you multiply by 1,000, that's going to be 625 milliamps. Okay? You see? Remember, to go from A to milliamps, you multiply by, no. 1 amp is 1,000 milliamps. Okay, yes. So you multiply by 1,000. Okay, so what is number 6? Okay, let's do number 6 just to review. Can you see here, is that big enough? Yeah. If it's not big enough, I can make it bigger. So the voltage, so that's a voltage, that's a current, and that's a time. So power is the energy per unit second. So it's just V times I, okay? So V times I, and what you get, so 12 times 210, very good, 2520 watts. So that will means joule per second, okay? So that means in 1 second, that appliance, it's a motor, it's a starter, is consuming 2520 joule. So in 10 seconds, of course, it's going to consume 10 times more. Does that make sense for everyone? Joule. That will be the energy consumed. So what is the equation? Energy equals power times time. So if you want the energy in joule, power has to be in watts and times has to be in second. If you want the energy in kilowatt hour, because that's what the electric company use to charge you, then you want the power in kilowatt and you want the time in hour. Is that clear? Now, 1 kilo is 1,000. Okay, so 1 kilowatt is 1,000 watt. So if you have watts, you divide by 1,000 to get kilo. Are you sure we didn't do that? No? Okay, I think that's easy, right? Okay, let's do to 63. Let's do number 2. Oh, that's easy. You are using Ohm's law. So you have the voltage. So you have a resistor here. The resistor is 15 ohm. And it's a cross circuit here, but we don't know much about the circuit. You know, somewhere maybe you have other component. Of course, you're going to have a power supply. So we don't know. But we do know that the voltage across is 75 volts. So you are measuring the voltage across. Okay. And you want to know the current going through that resistor. And maybe you have, you know, it can be a very complex circuit. All you have is this, the voltage across, and you want to find the current going through. And the voltage across a resistor, that's called Ohm's law, V equals Ri. Okay? So what's going to be I? 5 amps. Good. So this is true only for special loads. We call that ohmic load, meaning like light bulb, things like this. It's not true if you have an LED, for example. Okay, let's do number 3. Okay, very easy. Number 3. You can help each other, you can talk to each other. So here the load is a lamp, but the lamp is like a resistor. Okay, especially if they are the incandescent lamp. So you have the lamp and you have your 120 volt here. So what's going to be the voltage across 120? Okay, because it's just plugged into the outlet, so there is no other load to worry about. So the voltage drop is 120 and the current going through it is 0.5. So you can find the resistance, right? So Ohm's law, V equals Ri. So 120 equals R times 0.5. So R equals 240 ohm. Okay? The power, so power, I can do that different way. I can say P equals V times I. Okay, so that will work. The voltage is 120, the current is 0.5, so that's going to be very good, 60 watt. But because it's a resistance, I can also say that P equals Ri squared. Okay, that works only for load with a resistance R. Let's see if we find the same thing. R is 240, and then you have the current, which is 0.5, so 0.5 square. So what do you get? divided by 4, okay, because that's 1/2 square, that will be 1/4, and you height, you get also 60 watt. So that's an alternative. Another alternative is V squared over R. So those equations, okay, only for loads, something that consume energy and has a resistance R. This equation is for anything, power supply, any load. Okay, it's always V times I. So let's see if it is true. V squared will be 120 squared divided by 240. So what do you get? $120 squared divided by 240, 60. So it depends whatever is more convenient. If you want to go faster, if you have a resistance R, you can use this one, or that one. Okay? What else? Okay, I think you get it. Okay, I'm gonna skip number 6. I'm skipping also. How do you do that? A resistance 60 and you have a current through it of 0.4. How do you find the voltage drop? Very good, you multiply, right? And there is no other load to share the voltage with. Yes. So here I use ohms, so V equals Ri. Okay, only true for load. So V is the voltage drop across the load, R is the resistance of the load, and I is the current going through the load. Okay? You said that there's only one battery. What if there was two? Can you split that number now? So that's a good question. You mean if you have two load? Yes. So so if you have two load, that's what is coming next. Yeah, you will have. I think I did that something like this last time. If you have two load, it depends on the resistance, right? So for example, if you take a load of 10, okay, and I take another load here, and I'm going to increase the resistance to 50. I like all number. Okay, so one has more resistance than the other one. Which one do you think will have the largest voltage? Because the current is the same, right? The current is the same everywhere. The one with the least or the most? Because V most, right? Because V equals Ri. So if the I is the same, so it depends on R. So the one with the most resistance will take the most voltage. So this one is 50. Do you remember that? This one is 10. Let's measure the current. 0.15. Okay. The power supply is 9 volt. So let's take a voltmeter. So what do you think you're going to read here? The resistance is 10 and the current is 0.15. So what do you think the voltage is going to be? 1.5. Do you all agree? V equals Ri. So here I'm going to have 1.5. Do you agree? And how much is available from the power supply? 9. So what do you expect this one to be? 7.5. Okay? And let's check. 7.5. How do I know? Because 50 R times the current going through it 0.15 equals 7.5. Does it make sense? The voltage drop across a resistance equals to its resistance times the current going through it. So you never have this setup because the one with the largest resistance is stealing everything. It's stealing all the voltage to it. Okay, you see how much brighter it gets relative to this one. And it should be, it's not what you want, right? When you have a large resistance, that means you limit more the current, so you should get less power. But in that case, because they are in series, this one will get most of the voltage. Do you see that? Do you see that? It can get even worse if you increase the resistance even more, like nothing is left to this one, and this one is taking everything. Okay, so you can verify 120 times 0.07 equals 8.31. Is that clear? Of course, if you have the same load, of course, there is no favoritism, right? So 4.5 here, and then here you have 4.5, so that's going to give you 9. Okay, so now they share because they have the same load. They are the same load, so they have the same appetite. Okay, so we did 6. Okay, 64. About schematic, let's do number 2. Try to do a schematic for this problem here. So you have the schematic for a battery, for a switch, for a voltmeter, for an ammeter, for a resistor. Okay, so just about drawing. Okay, so you want to use those schematic. So then you know how to read schematic. So you want a 60-volt battery. So that will be the schematic for a 60-volt battery. Why don't you try to do it on your own? I see people staring. Don't stare. So 60 volt. And then you want a resistor. So I'm going to put a resistor here, 12 ohm. And then the ammeter is to read the amps. But it has to be part of your circuit, okay? Because it's like the charge has to go through the device to count 1, 2, 3, 4, 5, 6, right? You have a little lamprochon, I don't know what it's called, like a little thing here inside counting the charge. So it has to be part of the circuit. Maybe you want to include a switch here that you close. And then you want to draw the current from plus here going through the resistor and back to base. Is that clear? So if you measure the voltage here, I can add a voltmeter. Okay, it says voltmeter. What's going to be the reading here? What's going to be the reading? Hmm? 5? Why 5? Yes, so your 5 will be for the current. Okay, yes, you're right. So for you're right. So for the current, yes, that will be the first question I skip. So in that case, yes, you're right. So the current will be 5 amps. You're right. But the voltage here across the resistor will be 60 volt. Okay, because there is no other load to share with. Okay, so yes, you're right. I skipped the first question. Okay, is that clear? Bless you. Ok, 3. Okay, let's do this one quickly. Number 3. Okay, so you want to have a battery. Okay, so long leg plus minus. Okay, and then you have a resistor, 6 ohm. And then let's put a switch somewhere. And then you have a ammeter to measure the current, and it says the current here is 2 amps. The voltmeter, so I want a voltmeter across the battery here. So I'm measuring across the battery. So you're going to have current flowing. Go back. Okay, so can I find the voltage across the resistor? The voltage equals Ri, right? Ohm's law. So that's going to be 32 volt. So the voltage here of the power supply has to be 32 volt. Is that clear? It's not hard. Okay, make sure not to forget everything from one class to the other. And you have a book, so you want to make sure to read the book. Okay, number 3. Okay, let's do something a little bit more challenging. Not much. When you say, you all know, when you say 20% off, okay, so that means 20% means 0.2. Off means multiply. So 20% of $1,000, you go 0.2 times 1,000. So off means multiply. Okay, so that was the half a second math. Okay, let's try to do number 3. You can help each other and discuss. Okay, so it becomes more dynamic. Okay, so 100 watts. So this is what? What is the physical quantity here? Power, very good, okay? So we have the power of a light bulb, and it's very important, like any job that you're gonna have, you need to understand power, right? If you go to medical field or healthcare and things like that. So you always have a reading, even in your laptop. On your laptop, it's gonna tell you the wattage. So wattage here is 100 watts, so 100 joule per second. However, here we are talking about the old light bulb, okay, incandescent light bulb, and they were 20% efficient, which means that only 20% of the energy is converted to light. Okay, so what does it mean? It means that 20% is light and 80% is what? Huh? Heat. Of course, remember the old light bulb, you could not touch it, you had to take like something, otherwise you will burn your. But they were, you know why? They were in a way good, because heat, maybe from chemistry, or I don't know, what type of electromagnetic wave gives heat? If you have a reptile, for example, and you want to keep your reptile hot or warm, what kind of lamp do you use? Huh? Yes. So what do we call that? No, the lamp that you use to warm up. Infrared. You have those special infrared lamp. Okay, they are red. I know because my son has a French gecko. So no, not French. But leopard gecko. That's what it's called. Infrared. I see French everywhere, but no, gecko are not French. They come from Afghanistan actually. But infrared. Okay, so infrared is heat. And is infrared good for us? Yes, because actually the studies show that infrared goes inside your skin, through your skin, and it's good for the mitochondria. Okay, it's boosting the mitochondria. So infrared is very good. So it was good to have those lamps, but now they have been phased out. So I'm taking a tangent. So sorry. Okay, so 20% is light. So how much power is that? 20%. 40 watts. 20 watt, thank you, 20 watt. Okay? So what does it mean, 20 watt? It means that the lamp, it's gonna consume 20 joule for every 1 second. Okay? So to produce light. Is that clear? So in 1 minute, 1 minute is how many seconds? 60 question mark. So the energy, okay, that the light bulb convert from electrical energy to light energy is going to be is that 600? No. Oh, it's 20. Thank you. Thank you. What's your name? Thomas, right? We are missing Nathan here. So it's going to be 1200 joule. Is that right? Okay. What does it say? How many joule the light bulb produce in as heat? Can you do that? Yes, you're right. How much? Exactly. Who said that? What's your name? Miguel? Mattel. Okay, so that will be heat and that will be light. Do you all agree with that? Because here you're going to have 80 watt. So all together in 1 minute, your light bulb is going to consume 6,000 joule. So that will be how much it's going to consume. Okay? Is that clear? So, or you can say 100 watt. Okay? So that means 100 joule in 1 second. So in 60 seconds, you're going to have a question mark. So that's going to be 6,000 joule. So some of it will go to light, some of it will go to heat. Okay? So conclusion, don't be afraid of infrared. It's a heat wave. Okay. Okay, so this is the steps to convert, to find the energy in kilowatt hour. So you will be able to pay your bill. But we already talked about that. So I'm gonna skip here and take an example here. So let's take this example here. Number 1. Okay, if you have any question, let me know. And make sure to go over your textbook. I think the chapter is 19, I'm not sure, or 21 or 20. Last time I show you. So this one is easy, right? A, what's going to be the power? 240 watt. Do you all agree with that? Power is the voltage times the current. So it could be the power delivered by a power supply or the power consumed by a load. Now we want the energy in kilowatt hour. So again, I'm going to try that again. If the energy is in joule, then the power has to be in watt, and you multiply by the time in second. However, the electric company don't use joule because otherwise it's going to be a big number and everyone will freak out. So instead, they use kilowatt hour. So in that case, it's still power times time. The power has to be in kilowatt and the time has to be in hour. Okay? So So how long? 30 days and 5 hours per day. It says go forward. I go forward. Are you doing it? Don't stare. So we need to find the power in kilowatt. So how do we find kilowatt? Very good. You divide by 1,000. Exactly. So watt to kilowatt, you divide by 1,000. So that's going to be 0.24. And then the time, I did a mistake? No? And the time in hours, so you have 5 hours for 30 days. So every day 5 hours. So it's going to be 30 times 5. So that will be the total amount of hour. Too much TV here. 5 hours per day. So what do you get? Very good. 36 kilowatt hour. Is that Cora? Yes. 36 kilowatt hour. Is that clear? So it's a unit for energy. Now the cost of energy, I don't know where it is, but it's 80 cents per kilowatt hour. Last time we looked in Miami, I forgot if it's 50 cents or something like this, 15 cents. So how much you gonna pay? Okay, so 80 cents for 1 kilowatt hour. So 36 kilowatt hour, question mark. So you cross multiply, divide, and you get 28.8 cents. Very good. Huh? So if you want to save 30 bucks per month, don't watch TV. You're gonna save that amount. Okay. Let's go back to the website we were looking at. Let's go back to here. Okay, let's try to do this one. 10 cents per kilowatt hour. That's an old website. You have an 800-watt hair dryer. You have a lot of hair. 30 minutes to dry your hair. That's yeah, right? It's 30 minutes. You're gonna fry them. You're gonna fry your hair. Okay. How much does it cost? So let's find out in kilowatt hour. So it's the power in kilowatt times the time in hour. Okay, so do it. It's gonna be 0. So you see here you have to divide by 1,000. So it's gonna be 0.8 times half hour. So half hour is 0.5. Did I do it right? Half an hour, right? 0.5 hour. I want to multiply kilowatt by this, which is 0.4 kilowatt hour. And if it's 10 cents per kilowatt hour, so you multiply this by 10 cents, which is nothing. So 0.04, which is 4 cents. Any question? Right? Anyone with me? Okay, so this I'm gonna skip. Okay, I want to connect to what you are doing in other classes, so thermodynamics. Not hard. So if you have any question, let me know. Just want to move this. So maybe you learned that in, I'm sure in chemistry, it takes a lot of energy to heat up water. Okay, it takes a lot of energy. Actually, if you want to heat up 1 kilogram of water, okay, and increase its temperature by 1 degree Celsius, it's gonna take you. It's gonna take for about 4,000 joule. Okay, and 4,000 joule is one food calorie, so it's 1,000 chemistry calorie. Okay, so that's why the water on earth is so important, because even though it can be very, very cold, because it takes so much time for water, okay, to cool down, for example, then it will keep us warm. Or the opposite, because it takes so much time for water to warm up, it's going to keep us cool. Okay, so all the cities, for example, by the ocean, it's always be like more or less moderate, because it takes so much energy to change the temperature of water. Okay, is that clear? So you have this equation, the energy that you give to water, okay, so the energy consumed by water, okay, um, will raise the temperature of water, and we have this equation. Okay, so the energy that you give to water will be equals to the mass of the water in kilogram times that constant here times the change in temperature in degrees Celsius. So it means that if you want to increase the temperature by 1 degree Celsius of 2 pounds of water, you need to provide one food calorie of 4,000 joule or 1,000 little calorie. This is the chemistry calorie. So it takes a lot of energy to change the temperature of water, which is good because we are mostly water, okay? Otherwise, we'll be boiling out as soon as you go outside in in the summer here, or freezing if you go to Illinois. Now it's like minus 120 Celsius. Okay, so now you can try to do this. So it's an electric stove that you use to heat up water. So an electric stove, you can think of that as a load, and the resistance is 11 ohms. You are using 220 volt, so I guess we are in Europe, and find the current going through the resistor. So that's, you are using Ohm's law. There is nothing new under the sun, just use Ohm's law, V equals Ri. Okay, so the voltage drop is 220. Okay, so 220 equals the resistance of the load is 11, and you have the current going through it. So what do you get? 20 amp. Yes? So 20 amp going through the electric stove. An electric stove is basically a resistance, B. Okay? So what's going to be the energy used in 30 seconds? So first, when they ask you to find energy, you need to find the power, because power is just the energy in 1 second. So let's find the power. What's the equation for power? Very good. V times I. Exactly. So it's going to be power supply is 220 times 20. Watt. Is that right? Yes? Okay. So that will be Remember, that will be energy. That will be the energy for 1 second. That's the definition of power. So if you are using it for 30 seconds, so you multiply by 30, right? Okay, so it's going to be more energy. So don't stare. And you're going to get very good joules. Okay, so that's how much energy the stove provides. Okay. However, um, however, so you want to use that energy to heat up a mass of water equals to 1.2 kilogram. But only 70% of the heat is used to heat up the water. The rest is lost to the environment. You are heating the kitchen, for example, instead of heating up the water. So what should I do now to find how much energy is used for my water? Very good. Okay, so each time you have a percentage, of means multiply. So only 70% of that energy delivered by your stove is being transferred to the water. Do you understand? So it's like if you want to understand, you have like a stove. So this is like a big resistance here. So this is connected to 220 volt. It's gonna provide heat, but only 70% of this heat is used to heat up your water. So you have like a kettle here, you have water inside. Only 70% here is used. The rest is lost to heat up the kitchen. Are you with me? Okay, so find how much is 70% of that. Okay, so 70% of the energy, it's gonna be 92,400 joule. Yes? Okay, so this is the energy transfer here to your water, which is 1.2 kilogram. Okay, now you can answer the last question. Okay, so the energy consumed by water will be equals to the mass of the water times this number times the change in temperature. So the goal is to find the change in temperature. So the water is going to use that energy provided, okay, to heat up. And we know that the 1 degree Celsius will change if you provide 4,000 joule to 1 kilogram. So you just use this equation, okay? So what do you get? Just plug it in. So how much energy is available? 92,400. That energy is going to be delivered to 1.2 kilogram of water. Here you have a constant. And here you have the change in temperature. Yes. So what did I use? I use 7% means 0.7. So I do 0.7 times 7% of the energy. So 0.7 times this. Okay? The rest of the energy has been lost to the environment. So you isolate delta T, what do you get? Exactly, 18 degrees Celsius. Huh? Didn't you do that something like this in chemistry? Huh? Something like that when you give heat, like for to a metal, for example, you can find its change in temperature. You have very cool lab to do with that. Any question? Okay. And now we want to heat up air. Look at those equations here. What is the constant that you have for water? About 4,000. Okay, here you have what? 1,000. So which one is easier to heat up, air or water? Air, very good. Okay, water, you need to get a lot of energy to change its temperature. So even though it's freezing outside, the water will not be freezing, the ocean, for example, because it takes so much energy to change the temperature. So here you have only 1,000. Okay, so let's apply the same methodology and see what you get. Same thing. So apply the same steps. So you can talk to each other, you can help each other. It's very important that you find a study group, that you make new friends. So you talk to each other, help each other out. Yes.
Slight question, does it matter? Power and watt or kilowatt?
So in that case, you don't want kilowatt. It's a good question. Okay, it's a very good question. In that equation here, the energy is in joule. So you need to use watt. Okay, because energy in joule, then the power is in watt, and the time is in second. So what do we use kilowatt hour? It's when we deal with the electric company and we want to know how much we're gonna pay. Okay, but in that equation that you have seen in chemistry, probably the energy is in joule because this 1,000 is in joule. So it means it takes 1,000 joule, okay, to change 1 kilogram of air by 1 degree Celsius. That's what it means. Okay, so A. So how much energy in half an hour? So energy in joule will be power 500. Half an hour, half an hour. How much is half an hour? So 30, 1800, yes. Because 30 minutes and 1 minute is 60 seconds, right? Uh, is that right? 500 watt times 30 minutes and 1 minute is 60 seconds. So what do you get? 90,000? 9,000? Ah, 9,000. 900,000 joule. Thank you. 900,000 joule. Okay. And then the heater is used to heat a room containing 50 kilograms of air. Blah, blah, blah. 50% of the thermal energy heats the air of the room. Okay, so it means we are not using the whole amount of energy, but only 50% of that, right? So 50% of 900,000 is used to heat the air. So it's only 50% efficient. So how much is off means you multiply. So how much is that?
400.
Exactly. Joule will be used to heat the air. So then you just use that equation here. So you plug it in. So you have 450,000 equals 1,000 is a constant times the mass of the air is 50 times delta T. So il y a 1, 2, 3, 4, 1, 2, 3, 4, 9. 9. degrees Celsius. Okay? Okay. Okay, let's see here. We did that. 67. Let's talk. I had another problem here, number 6. Will are we going to do it, or you know how it works? So how much energy? So 60 watt, 60 watt. If you want to find the energy in half an hour, you multiply 60 by 1800, right? So that will be the energy in joule. And then, okay, let's try to do that. Because it's good to have sometimes to work with percentage. Well, okay, let's find out how much energy altogether. It's going to be 60 times 30 times 1800, right? Is that right? So 60 because it's 60 watts, 60 times 30 minutes, and 1 minute is 60 seconds. So you get 108, 1000 joules. Did you get that? Yes? So that's how much energy the power supply is providing. However, a light bulb is only 12% efficient. So it means what? That 12% is going to be what? Efficient means what is a light bulb for? Is to provide light. So it means how much is left? Very good. So 88% is just heat. And what is heat? What type of wave is that? Infrared. Okay. You can feel it. Infrared is warm. It's not dangerous, okay? So we're not talking about UV. You also have UV lamp for your gecko, but this is infrared. So they want to know how much heat. So do I use the 12% or the 88%? 88, okay? So it was tricky because you had to find the 88 here. So you're going to do 0.88 times 108,000 joule. So that will be thermal energy. Huh? You said something? 95. You raised? You say 95. Hi, what's your name? Steven. Yes. So this is thermal energy. Just a parenthesis, heat, it means it's in being in transfer, okay? But that will be the thermal energy. Heat is energy in transfer. Okay? And again, all those you will find the solution in Dropbox, okay, tutorial. So about the resistance, you see, if any wire, like I have a wire here, you see, it has its own resistance. Okay, if I increase the length of the wire, what do you think is going to happen to the resistance? It's bigger. Very good. Okay, so it makes it's like you're making even harder for the charges to move. Okay, so resistance is proportional to the length, okay, of a wire. Okay, so that's what you see. The resistance here of a load or a wire here is proportional to the length of the wire, and it's inversely proportional to the, so here it's just the resistance, okay? So before you apply or you have a current, what do you think A stands for? The cross, the cross section, right? The area. So does that make sense that if it's like a pipe, if you have a very large pipe, you're going to have more current flowing. If you have a very narrow pipe, you're going to have less current. Does it make sense? So if you have a wire, thicker is the wire, less resistance it will offer to the current flowing. So that's why if you have the big appliance that consume a lot of energy, you're going to have a very thick wire. Okay, the thickness of a wire, an electric wire, it's called a gauge. Okay, so a resistance of a wire like this is proportional to the length, inversely proportional to the area. So if I ask you, if you take a wire, okay, you multiply the length by 3, what's going to happen to the resistance? This is going to be multiplied by 3. But if I increase the area by 3, the resistance will be divided by 3. Okay, so this is called a cross section. And here you have a constant, it depends on the material. Okay, so it's called the resistivity. So for example, the best conductor is silver. So that number here, it's going to be very small. And then, of course, silver will be too expensive if we have all the, I mean, we will get a lot of stealing. Already they are stealing copper in some places. So imagine this was made of silver. It will be a disaster, right? Everywhere they will cut out wires, too expensive. So now we use copper. Gold is not bad, but not as good as copper. Okay. And of course, lead is not great, but you don't want wire made of lead. And then here is the opposite, right? So these are very, very large resistance, like the human skin. Okay, so that's why if I told you, even if you do a shortcut with your car battery, if your hands are very dry, you should be okay. You're not going to be electrocuted because we have a very large resistance with our skin. Okay? Of course, if you apply a very large voltage, if you put your fingers in the outlet, that you should never do, the skin will not protect you. But usually, human skin has a very large resistance. Is that clear? So it's just a constant that you have here. Okay? So something to keep in mind. For example, you have those portable heater, and those portable heater is just made of wire. So if you open it, it's going to be looking like that. Okay, it's just wire and wire and wire. So that will be the resistance. And when you apply a voltage to it, they're going to turn that energy just into heat, into infrared. And if you increase even more, the voltage or the current is very large, it's going to start producing light because it's so hot. Okay, so that's not good because you don't want that to be as a light bulb, you want that as to be as a heater. So anyway, those devices, they drain a lot of current. So you want to make sure that you don't do that. Why you should not do that? Because this wire is relative to this one. Is it thicker or thinner? Thinner. So the cross section is smaller. So the resistance is higher. So what's going to happen? All the electric energy is going to turn into heat and you can start a fire. You're going to start a fire. So you want to be very, very careful when you are using extension that you have the high current for it. Okay. So for example, those very thick wire, they can take 120 amps, but those very thin wire, they cannot go over 20 amps. So if you are using 20 amps here, when this one is draining like 30 amps, it's going to be a problem. So the thickness here, the area, the cross section is called the gauge. Is that clear? So if you increase the thickness, if you increase the cross section, you decrease the current and you're going to have less energy that will turn into heat. Okay, because remember that power equals RI squared. Okay, so for the same resistance, when you have a load, which is a resistance, if the current is multiplied by 2, the power will be multiplied by 4 because it's a square. Okay, so now we're going to talk circuit in series. Let me start maybe with a simulation. Let's see. Here we already have that. So I'm gonna take a 10 ohms. What's gonna be the current? 0.9. I'm gonna take 120 volt. Boom. Wow. 120 volt. What's the current? 12. So what we call a circuit in series is when we have more than one load. So let's take the same load here with 10. The resistance is the same. So you have 10 here and 10 here. What's happening to the current? It went down. Exactly. It's divided by 2. So if you have the same load, if you have twice as much as load, okay, the current will be divided by 2. What's going to happen to the voltage is also going to be divided by 2. Okay, so you're going to have 60 here, and then you're going to have 60. Is that clear? So they are not happy. They are not as bright as they are supposed to be. Now, if I add more load, okay, so now if I have 3 loads here, you see? Very good. The current has been divided by 3. Okay, so I have 3 times less. Listen to that. I have 3 times less current. Are you with me? What's happening to the voltage? It also has been divided by 3. Okay, because here I have 120 and now it's 40. So listen, I have 3 loads. All the loads are the same. The current is divided by 3 for each load. The voltage is divided by 3 for each load. So the power will be divided by 9. 9. Okay? So it's not good. In a house, we never have that. Okay? Otherwise, it's not going to work properly. Is that clear? Plus, if one of them has a large resistance, okay, it's going to take, ooh, look at this one. It's taking everything. Almost all the voltage here is taken by this one because it has such a big resistance. V equals Ri, 102. So definitively, those are not happy. Okay, you see how it works? So I'm going to show you how to solve, it's called a circuit in series. Okay, let's go back to this one. Let's go back to 10 ohms. So they are all the same. Okay, can you read the current here? 4. Okay, and the voltage here is 120. How much is each resistance? 10 ohms. So does that make sense to you that I can remove this one? Okay, I can remove this one. Okay, and if I want the same current, what's going to be my resistance? 10 and 10 and 10, 30. Okay, it's like a game. So you can replace 3 resistances by 1, and all you have to do is to add up the resistance. So you can play with that. And let me show you now how we solve those kinds of problems. Here you have a circuit in series. And let's say this is 1.5. Okay, this is 1.5. So that will be the schematic for it. You have the power supply and you have 3 loads. And I will show you my trick. I have a special trick to solve circuits in series. I cannot move it. Okay, so let's do that together. So the goal is to find everything about that circuit, okay? So is to find what is the voltage drop across each load, and the current will be the same everywhere. Okay, it's going to be the same here, it's going to be the same here, and it's going to be the same here. And the voltage drop here, how much is from the power supply? Do you remember those C battery or D battery? 1.5, so 1.5 volts. So the way you do it is the following. You start with 1.5. It's very much like a height. And you follow here. Oh, I have a load. So I'm going to make my load here 10 ohm. Pum, 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 pum. Ah, I have another load. Tum, 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 tum. Okay. Okay. And then another one. Pum, 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 pum. And then I go back to base. So first of all, imagine its height. Because they are all the same load, what do you think the voltage drop is going to be? 0.5. Okay, so that means you drop by 0.5, you drop by 0.5, and you drop by 0.5. Because they have the same appetite. The current here will be the same. Okay, because there is only one way to go. You go from high, boom, to ground. So it's like a pipe. Now, the way we do it, or I do it, you can say here, everything happen like you have a big zigzag. So zigzag, 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 zigzag. Okay? What do you think the resistance here will be? 30. Okay, and the resistance exactly what it is. It's like a wire that is twisted and twisted and twisted and twisted. Okay, and you have the current here. So what's going to be the voltage drop here? From here to there? 1.5. Imagine it's something above the ground. Okay, you start with 1.5. Boom. So this is 1.5. So can we use Ohm's law to find the current? Right? So 1.5 equals 30 times I. So I will be, huh? 0.05. Exactly, 0.05 amps. Okay, or if you want milliamps, 1, 2, 3, so it's going to be 50 milliamps. It depends on the multiple choice. So sometimes it will say 50 milliamps. So you know how to convert. So 0.05 amps here. And then you go one step back, which means that's going to be 0.05 amps. Does it make sense? So it's a mathematical trick to find the current. So let's find the voltage drop. What's going to be the voltage drop here? 10, use Ohm's law. The voltage drop of 10 ohms and the current going through it is 0.05. So that's going to be 0.5. Okay? You multiply 0.05 by 10. How much is that going to be? 0.5. That's a drop. It's a voltage drop. And that's going to be 0.5. Does that make sense? 0.5 plus 0.5 plus 0.5, it's going to be 1.5. Okay? So that's the trick. So in the book, not going to use the same approach, but you get the same thing, okay? They will stick with that schematic and they will draw the current flowing through them and then they apply Ohm's law. Okay, so here you can see it starts with 1.5 volt, boom, it's falling by 0.5. How much is left? 1 volt. So it means if you measure the voltage between here and the ground, you're going to measure 1. And then boom, it's dropping again by 0.5. How much is left? 0.5. So you really have to think voltage as the height. Okay, you have the 1.5, boom, you drop, boom, you drop, boom, you reach ground. And the way to do it, you replace all the resistors here by a single one. That's the trick to find the current, and then you go back. Okay, so it says play with the simulation. Oh yeah, because I forgot we have the resistors, right? Okay, we have 4 minutes. Let's try to play with it. So if you can, if you have it, 30 volts. So for the homework, you will have to, I mean, it's fun, right? So 30 here, so 30 volt is the power supply. And then you take 3 resistors, 1, 2, 3. Okay, so each one of them is 5, so I'm going to take 5. 5, and here it's going to be, can I go faster or no? I don't know if I could copy. Can I copy and paste? No. So can you predict the current? What's the equivalent resistance here? Huh? So you have 5, 5, 5, 5. So you can replace the 3 of them by 15. And here, the voltage here is 30. So what is your prediction for the current? 2. It's 2 amps. Do you understand? Now, they are all the same, so they're going to have the same appetite. So what's your prediction for the voltage across? So you have 30 volt, the same appetite, so it's going to be 10. Excellent. Very good, 10. So 10 across here, okay, and then 10 across here, and 10 across here. You see how it works? Okay, so here you drop by 10, and then here, by the time you get here, you drop by 20, and everything is 30. So all the drop is 30 volt. Okay? Okay, so you can play with that for next time.